Okay, welcome to the last session of PLSS 2025. So we will start with a talk that has two authors. The talk will be given only by Jaehyun, but I would like to introduce Sukyoung as well. So Sukyoung is a professor in the School of Computing at KAIST in South Korea, and she currently serves as the head of the school. Sukyoung spent some years at Harvard and also worked at Sun Microsystems. Her research expertise is in programming languages, especially JavaScript, and also program analysis. Sukyoung led efforts to make JavaScript the first major language whose official specification is both type-checked and is executable via mechanized testing. Sukyoung has also contributed significantly to the SpecTec. We heard a presentation earlier today by Andreas, applying mechanized semantics to WebAssembly. Her community service is equally notable. She is co-chair of ACM SIGPunk Cares and has held key roles in major conferences like PLDI, POPOL, ICSI, Splash, and ICUP. And Jaehyun Lee is a master student at KAIST, working together with Sukyoung on the SpecTec. He is the primary contributor to the P4-SpecTec project, which mechanizes the P4 language specification using the SpecTec DSL, ensuring we would have one unified source of truth across formal specification, prose, interpreter, and the test suite. And that is what he will be talking about today. So let's welcome Jaehyun.
Thank you for the introduction, and also thank you for joining this talk in the Friday afternoon session. So today I'll be talking about P4-SpecTec, which is a project aiming to mechanize the language definition of the P4 programming language. Our project title can be naturally decomposed into two components, P4 and SpecTec. P4 is a domain-specific language for the networking domain, and SpecTec, as Andreas has given a keynote talk this morning, is a language mechanization framework. And put these things together, our main objective is to adopt language mechanization into the P4 language. And this talk will be organized along three core questions. So first of all, why do we need language mechanization in the P4 language ecosystem? And understanding the necessities, we want to discuss how to accomplish that goal by designing and implementing P4-SpecTec. And finally, I'll discuss several benefits that P4-SpecTec can bring to the P4 community. But before getting any further, let me very briefly explain about the P4 language. P4 is an acronym for Programming Protocol Independent Packet Processors. It is a domain-specific language to program network devices such as switches and routers. And with P4, we can specify how a programmable switch takes in an input packet and processes that within the switch, and then outputs the packet to an outbound port. And for the sake of this presentation, it is just enough to know that P4 is a statically typed language, so we would need a type checker. And also the core concept of P4 is imperative, like the C programming language. And viewing P4 from a programming language point of view, we can identify four main representations of its syntax and semantics. First, we have the official specification defining the syntax and semantics of P4 in informal prose. We have implementations, which are executable representations of P4. And the de facto implementation is the P4C reference compiler, which is written in C++. We also have tests coupled with the reference compiler, which are input-output examples for the language. And last but not least, we have formalizations, which describe the language in terms of very precise mathematical notations. And these can usually be found near academia. And the presence of multiple representation invites us to the question, are the four representations truly in sync? In other words, we are questioning, are they consistent with one another in defining the P4 language? In principle, they should be. However, in practice, they are not. And the main reason is that the four representations are maintained by different parties, and they evolve at different paces. And what contributes more to this inconsistency problem is that the P4 language is evolving. For instance, the official specification added generic structs and headers to the language at May 2021. However, this spec update did not perfectly land on existing implementation where the P4C reference compiler emitted an error when this generic type interacted with yet another language feature, which is type inference. This bug was identified and patched at March this year, which is very long after the specification update. And formalizations exist, but they mainly remain frozen before 2021, while the most recent version is based on 2024. And this kind of inconsistency is undesirable because it can silently lead the P4 language designers and developers and even hardware vendors into diverging directions. So the core challenge boils down to this question: can we at the same time evolve a programming language while maintaining the consistency between the different representations? And we claim that the answer is yes. There is an ultimate single source of truth that underlies different language representations, which we call the specification model. By specification model, we refer to an unambiguous and complete definition of the syntax and semantics of a language. So for instance, it can be a complete formalization or a definitional interpreter. And once we have this specification model, we can view other representations as instances of the spec model in different mediums. So we can view the document as a verbose version of the spec model, and implementations as instances of the spec model in terms of programming languages, and tests as concrete examples demonstrating the behavior of the spec model. And here is where language mechanization frameworks kicks in. Language mechanization framework allow for a systematic definition of the specification model by providing a domain-specific language called a meta-language to define the spec model. And once we have the mechanized spec model, we can automatically generate various backends from the single source of truth, which is the spec model. And with language mechanization frameworks, we can allow for a spec model to evolve while maintaining the backend representations consistent with one another. So far, we have discussed why do we need language mechanization framework in the P4 language ecosystem. And we will move on to the next discussion about how to accomplish that goal by designing and implementing P4-SpecTec. And for this, I would like to review the success stories from ES-Meta and Wasm SpecTec, which have been integrated into the official standardization processes of JavaScript and WebAssembly. First off is ES-Meta for the ECMAScript standard. Here we see the portion of the ECMAScript document defining the dynamic semantics of if statement. It is defined in terms of step-by-step prose pseudocode, and we can see there are several highly regularized prose patterns appearing in the specification, like let something be, if then else, and a return. So ES-Meta as a framework recognizes the regularized patterns and compiles the prose into an intermediate representation called IRES. So in ES-Meta, the meta language is the IRES language, and the compiled syntax and semantics definition is a specification model in ES-Meta. And an interesting backend of ES-Meta is its interpreter backend. So we have the JavaScript semantics defined as an IRES program. And when we can execute that IRES program with an IRES interpreter, then it yields a JavaScript interpreter as a result. And this derived JavaScript interpreter, when given a JavaScript program, will execute the semantics as per the ECMAScript standard to produce the correct result. And moving on to the next story about Wasm-SpecTec. As Andreas mentioned, the WebAssembly standard specification is quite particular in providing a dual representation of the semantics. So here we see the dynamic semantics of Wasm if instruction. Below, we see the formal specification defining the dynamic semantics in terms of formal reduction rules. And at the top, we see the prose specification describing step-by-step pseudocode of how to really execute the Wasm if instruction. These two representations are coming in different formats, but they are essentially describing the same thing. And of the two representations, Wasm-SpecTec chooses the formal reduction rule as its specification model. For this, it comes with a meta-language that is designed to closely resemble the textbook-style formalization in the Wasm formal specification. So below, we see the mechanized specification for the Wasm if reduction semantics. And we can see that it very closely resembles the formal reduction rule written in LaTeX. And for Wasm-SpecTec, the interesting backend would be the prose backend. So the specification model can be seen as a set of declarative reduction rules describing the semantics of Wasm. And it describes what the semantics is, but it does not necessarily describe how to evaluate the semantics in a computational sense. But it somehow derives a prose specification, which is essentially an algorithmic pseudocode representation describing how to compute the semantics of Wasm. This conversion from declarative to an algorithmic form is a non-trivial task in general, but Wasm-SpecTec makes it possible by assuming a shared format between the declarative inference rules, which is reduction rule operating on a stack machine. So at a very high level of abstraction, we can abstract away a lot of declarative rules in Wasm-SpecTec as a reduction from left-hand side to right-hand side accompanied by several premises. And Wasm-SpecTec has the built-in knowledge about this shared format of the declarative rules. And building on this, leveraging this knowledge, it converts the left-hand side into pop something from the stack pseudocode, premises into let bindings and if instructions, and finally the right-hand side into push something back to the stack pseudocode. And once we have the algorithmic model of the Wasm semantics, we can execute this prose pseudocode to get the Wasm interpreter backend, which is quite similar as what we did with ESMeta with the JavaScript interpreter backend. And we identified the underlying recipe for their success stories is that they had an authoritative spec model. The ECMAScript document and the Wasm formal specification are the standard defining the syntax and semantics of JavaScript and WebAssembly. And these have been the driver for the specification model and the framework designs of ESMeta and Wasm-SpecTec, where ESMeta models the ECMAScript standard in terms of IRES program, and Wasm-SpecTec models the formal rules in terms of declarative inference rules. And with this observation, we very quickly run into a fundamental challenge to apply our technique to the P4 language, is that P4 lacks an authoritative spec model. Recall the four representations that we've seen before. We have the official specification, but it's neither formal nor systematic. We have the de facto reference compiler, but it adopts a nanopass architecture where the language semantics is scattered through various compiler passes. So it fails to give a monolithic view of the semantics. We have tests, but they're naturally incomplete. And we have formalizations, but they're incomplete and also not up to date. So before even defining what the specification model of P4 is, we have to first identify an appropriate form for a P4-spec model. And then we have to design a meta language to express that P4-spec model. To find the form for a P4-spec model, we again review the two options that we've seen before, the declarative inference rules in Wasm-SpecTec and algorithmic pseudocode in ES-Meta. First, we have our algorithmic inference rules, and they excel in the abstraction level. So we have a very high abstraction level, so we can hide various implementation level details like memory management and explicit error handling. And also, it can enforce the spec writers to specify the semantics in terms of case analysis, because inference rules by construction disallow nested control flow. So typically, we don't write inference rules with nested control flow. We would instead have distinct rules that apply case analysis to the language semantics. But it comes at a cost that inference rules are not directly executable. And this is the particular reason why Wasm-SpecTec had to bake in the built-in knowledge about the shared format of inference rules to derive the prose and an interpreter. However, it's the same reason why Wasm-SpecTec currently cannot handle the static semantics, because the static semantics mechanized in Wasm-SpecTec are irregular in shape and also non-constructive in general. So it cannot generate a type checker. Take this transitivity rule, for example. To say that type A is a subtype of type B, we need to somehow find the intermediate type B. However, this inference rule itself does not give a clue how we should find the value type B in a computational sense. And moving down the axis of abstraction level, we meet algorithmic pseudocode model, as in the case of ES-Meta. It loses some abstraction, but it still can hide some implementation level details. And the good part is that it is executable, so it allows one to directly derive an interpreter backend. And for P4-SpecTec, we would like to propose a middle ground, which we call algorithmic inference rules. So these are a subset of inference rules that are constructive by nature, thereby allowing the inference rules to be directly executable. We accomplish this by adapting the Wasm-SpecTec meta language, so we can describe the inference rules with the meta language frontend, but we also enforce several constraints on the meta language to ensure that the inference rules that the spec writer is writing is actually computable. So let me demonstrate with an example. This is the P4 specification for the if statement. So it says it uses standard syntax and semantics familiar from many programming languages. So we understand what it means, but it's not formal in any sense. And it also puts a single constraint that the condition expression must be a Boolean type. And we mechanize that specification into P4-SpecTec model in terms of algorithmic inference rules. At the top, we declare the statement typing relation. It's just a schema for the statement typing rules, saying that under some context, we type check a statement to yield an updated context. And below, we define the typing rule for the if statement. Under the context C, we first type check the expression to get its type, and then check that the type is actually a Boolean type. And then we recursively type check the both branches. And then we finally result in the same type in context C without updating anything. And actually what just happened is that with intuitive sense, we have already executed this inference rule. And what just happened is that we somehow knew that the subject of the rule is the type in context C and the if statement. And the result of the rule is the same context C. And while reading the rule, we were able to track the computation and data flowing from the subject through the premises in order, and finally to the result. And to align with our intuitive interpretation, of the algorithmic inference rules, I'll illustrate several constraints that we impose on the SpecTec meta language to guarantee their algorithmic property. The first constraint is that we annotate inputs and outputs of relations. So here we see an input hint next to the statement declaration saying that the zeros and the first components are acting as inputs to the relation. By this, we constrain the interpretation of mathematical relations to have designated inputs and outputs. So in effect, we are interpreting relations as partial functions. And by this hint, the backend can actually know that the inputs and outputs are as what we expect. And the second constraint is that data should flow sequentially through the premise from the input and premises and to the output. And to check this condition, we have to carry on the known variables. So we first start with 4 known variables from the input of the rule, and we move on to the first premise. It's invoking another relation for expression type checking. And the 2 variables, C and expression C, are known variables, which are input to the relation being invoked. And from the known variables, we bind a new variable, type C, acting as the output of the relation. And here comes the third constraint that except for binding positions, all variables must be known beforehand. So if instead we somehow written a rule where an unknown variable occurs as an input to the relation being invoked, P4-SpecTec would reject this kind of mechanized specification. So it helps to forbid some types of existential premises. And let's move on to the next premise. It comes with a form of if x equals y. And actually the equal symbol here is ambiguous. It can mean either equality check or an assignment from x to y or vice versa. And for computation, we really need to disambiguate the overloaded equal symbol. And for this, we have to consult the known variables. So if the both sides are known, it must be an equality check. If only one side is known while the other is not, it should be a binding from known to unknown. And we reject all the other cases. So for this case, we know type C and the terminal symbol bool T, so it must be a comparison. But if we have written a spec in this format where we know type C, but we don't know type sum, we would interpret this as an assignment from type C to type sum. And we move on to the next premises where we recursively type check the both branches, and then we bind CT and CF, but result in the same typing context C. So we write the P4 specification in our meta language, and P4-SpecTec has some built-in constraints that checks the inference rules are actually computable. And coming again to the spectrum of abstraction levels, we think that we do hit the middle ground because algorithmic inference rules are constructive and executable, but it also retains the good properties from the inference rules such that it enforces case analysis, and it also helps to hide implementation level details. And further, it is a friendlier interface for the P4 community whose majority coming from a networking background rather than a TL background. And with our algorithmic inference model, we have defined the full P4-Spec model of the syntax and type system, excluding some very specific features, which amounts to 8.5K lines of code in our meta language. And I would like to very briefly discuss the benefits of P4-SpecTec. First, this is the grand vision of our project, where we want to generate an official specification, parser, type checker, interpreter, and a test suite from the single source of truth. Those in red are to-dos, and those are in green are functioning to some level. But by identifying the P4 specification model itself, we were able to find inconsistencies and ambiguities in the P4 language definition. So we reported 9 issues on the P4 specification, asking for more clarification, and 13 on the P4C compiler repository, where we catch some diverging behavior between the compiler and the specification. And also, we can derive a P4 type checker as a backend. So we can run the algorithmic inference rules to get the P4 type checker out of the mechanized static semantics. And we validated it with an existing P4C reference compiler's test suite. So for the positive test checking that it accepts well-typed programs, it passes more than 99%. And for negative test checking that it rejects ill-typed programs, it passes more than 98%. And a little bit more about the negative tests. So we can question whether the negative tests are enough. In other words, we don't want 100 tests checking very trivial free identifier errors. We would instead want the test suite to exercise all the different ill-type conditions defined in the P4 type system. So again, with the if statement typing example, we want to see whether there is an existing test case that triggers the violation of this condition. And also we would want to collect all these ill-type conditions over the specification. But manually doing so would, of course, not scale. But fortunately, we have the P4 specification model, which is complete, unambiguous, and also it is mechanized in P4-SpecTec, which allows to be executable and also manipulated by our framework. We build on 2 observations. The first observation is that we define the type system in terms of inference rules, where we omit the error states. But on the flip side, when we violate a conditional premise, that would roughly correspond to an ill-type condition. So if we violate the second premise here, it would be the test case triggering the violation that we've seen before. With this observation, we collected 1,083 ill-type conditions over the specification. And the second observation is that ill-type programs are typically one-off from well-type programs. So we mutate existing well-type programs to yield negative tests. So on the bottom left, we see a benign program. And this, when executed with our mechanized specification, would result in the second premise being satisfied. And this would be a promising candidate for mutation because it at least reaches the second premise. And we implement several random mutation operators, which mutates this program into the bottom right, which will actually trigger the violation of the ill-type condition. So out of 1,083 ill-type conditions, we've built a fuzzer around P4-SpecTec, and we fuzzed some negative tests. So we reach a 60% coverage over the ill-type condition, which is almost the double of the current status quo of the P4C test suite. And with the generated tests, we were able to discover 11 unknown bugs in the P4C front end, even including a seg fault. So language mechanization really brings benefit to the language ecosystem because mechanization allows for a systematic and automated processing over the language definition. So we would like to continue our effort towards generating more backends in hope of allowing P4 to evolve while maintaining the consistency between these backend representations. And let's zoom out for a moment as a final remark. Our effort can be abstracted as language mechanization evangelism. So we have the machinery with us, the ES Meta and Wasm SpecTec, and with these 2, we are approaching real-world specifications to really help them keep consistency. For example, we have P4 and many more languages, but the problem is that they come without a clear specification model. So what should we do with this problem? We want to approach many languages without a clear specification model. So here I refer to the famous Feynman problem-solving algorithm. So we should first write down the problem, think very hard, and then write down the solution. And a takeaway from this talk, I believe, we can refine the fine-mind problem-solving algorithm to the language mechanization context to first pick a programming language that we want to apply mechanization to, and think very hard in the design of the specification model and the meta language, and finally write down the mechanized specification. And we do think that there are a lot more to do, and we should discover them. But I think this is the main takeaway that I wanted to convey in this PLSS workshop. And with this, I conclude, and I'd be happy to take questions.
Thank you very much. Thank you very much. Questions?
Thank you for the talk, very interesting. I think it's really fascinating that you're making changes to SpecTec that, to me, makes it seem like you're approaching theorem proving. You're turning these rules into constructive proofs almost. You're going kind of part of the way, and you're turning SpecTec into an interactive theorem prover a little bit, right? It's now shouting at you if you don't have things marked input and output because they cannot be interpreted as functions. And it makes me wonder if I can imagine there's maybe reasons you wouldn't want to, but maybe there would be reasons you would want to explore coming from the other end. Perhaps there exists like a library you could write in Isabelle or Cork or something, which could be used much like you're using SpecTec.
I think that's very interesting. And for me, actually, proving properties about P4 is not at my plate at the moment, but I think that's very interesting. And but about the theorem proving, that viewing P4-SpecTec itself as an interactive theorem prover, I think it is not quite what P4-SpecTec aims to be at the moment. Yeah, but did I answer your question?
Yeah, thank you for the talk. Not really a question, but just like an observation in continuation to what the previous question was about. Like, to me, what you did with your algorithmic inference rules, it looks like a side child of like relational programming, because basically you're just saying you can define relations, but the limitations that you have allow them to be executable, and that's precisely what relational programming is about. Like, you put even more restrictions because like a lot of the, like, you don't want to, because like in relational programming you can execute the program from the output to the input, and here you probably don't want that. Maybe you do, I don't know, but like it's just like, I would say it's closer to that domain than like proofs, because you want the thing to be executable to get all of the artifacts that you need, and like proof languages don't give you that very often. But yeah, that's really cool work.
Yeah, I mean, I can also comment on that, and I agree, right? This is like the input-output thing is exactly like modes in some of the logic programming languages, and of course we know that we can like infer these things, and to some degree that's what's happening in Wasm SpecTec. It tries to infer basically some of these things and transform the premises in a way that, like, currently we're doing that in a somewhat ad hoc fashion. We're hoping to make that a bit more well defined, I guess. But we are also moving in that direction where we want to define kind of like a subset of the IL that has these properties, and then have passes that kind of transform the more general input and infer like the rewriting you have to do to achieve that. So I think they don't have to be mutually exclusive. And maybe to follow up with the other question, there are of course reasons sometimes you want to have that kind of thing. Like you showed the transitivity rule, right, for subtyping. That's how you want to write it, because it makes certain proofs much easier. You can do an algorithmic subtyping relation, but it's much more ugly because you have to fold in subtyping and subsumption everywhere to make that algorithmic, and that's a well-known kind of thing. Yeah, so there are drawbacks and trade-offs usually.
Any more questions? If not, then let's thank the speaker again. Thank you.